As we have shown that the efficiency of half-wave rectifier is lesser, it is 40.6%. So to improve the efficiency of the half-wave rectifier, we use the full-wave rectifier. The circuit diagram is having the AC voltage, which is the input voltage, applied at the primary coil of the transformer. The transformer is center tap transformer. Across the terminal A and terminal B, we use two diodes. First diode is say D1 and another is D2. The common terminal is say point C, and from the center tap to the common terminal C, a load resistor is connected across which we take the output voltage. Now first we draw the waveform of the voltage at the terminal A. This is VA with time. Then voltage at the terminal B with respect to time, and then output voltage, that is the voltage across the load resistor. The voltage at the A is sinusoidal AC voltage having the alternating positive and negative half cycles. Then at the point B, it has the same shape but out of phase. That is, at the point B, the voltage will be first negative half cycle, then positive, then negative, and then positive. In first half cycle, VA is having the positive half cycle, so D1 will be in conducting state. So for first half cycle, D1 is conducting. Then in second half cycle, it is the diode D2 which is conducting. Then in third half cycle, it is again D1 is conducting, and alternatively D1 and D2 are conducting. As in first half cycle, D1 is conducting, so voltage at the output will be similar to the voltage at the point A. And in second half cycle, D2 is conducting and output voltage will be similar to voltage at the point B. In same way, we will have the output voltage for the different cycles. Here we can see that the cycle of the input voltage at point A is having the period T. Similarly, voltage at B have the period T, while the output voltage has the period T by 2. So we can say that if input voltage at point A is having the frequency 25 Hz, B is also having the 25 Hz, while the frequency of the output voltage will be twice of the input voltage, that is, it will be 50 Hz. Now we have to find the DC voltage and the RMS voltage of the full wave rectifier. So DC voltage, or also called the average voltage, will be equal to 1 by period, and period for the output for full wave rectifier is T by 2, integral 0 to T by 2, and the shape is sinusoidal, that is Vm is the peak voltage into sine omega t dt. This will be equal to 2 by t. Vm is constant taken out. Then integral 0 to t by 2 sine omega t dt. And we write it as 2 Vm by t. Integral of sine omega t is minus cos omega t by omega. 0 to t by 2 are limits. Minus 1 by omega is constant, so it is taken out. It is minus 2 Vm by omega t. And then remaining is cos omega t 0 to t by 2. Now, omega t is equal to 2 pi. So we substitute value here, minus 2m by 2 pi. And then first put upper limit, that is cos omega into t by 2 minus cos and then 0. Cos 0 is 1 and omega t is 2 pi. So this will be simply cos 2 pi by 2, that is equal to cos pi, that is equal to minus 1. So this will be equal to minus 2 Vm by 2 pi into minus 1 minus 1. That is equal to, this 2 and 2 get cancelled. So it is minus Vm by pi into minus 2. So we can write it as 2 Vm by pi. Hence, DC voltage or the average voltage of full wave rectifier is 2 Vm by pi. Now we have to find the RMS value of the voltage for the full wave rectifier, and it will be equal to square root of 1 by period, this is t by 2, into integral 0 to t by 2, and the voltage is Vm, this is the peak voltage, sine omega t whole square dt. We have to take the root mean square value, then means first we have to take the square of the input voltage, then we have to take the average, and after that square root. So it will be equal to square root of 2 by t into integral 0 to t by 2 Vm square sine square omega t dt. This is equal to integral of 2 by t. This Vm square is constant, so taken out of the integral, remaining is 0 to t by 2. And sine square omega t can be written as 1 minus cos 2 omega t by 2 dt. This will be equal to square root of 2 by t into Vm square. Here 2 is also constant, so taken out, and remaining is 0 to t by 2, 1 minus cos 2 omega t dt. This is equal to 2 and 2 get cancelled, so remaining is square root of Vm square by t. Integral of 1 is t, and integral of sine cos 2 omega t is minus sine 2 omega t by 2 omega, and limits are 0 to t by 2. Now we put the limits, we will have Vm square by t. First upper limit, it is t by 2 minus sine 2 omega, and small t has the limiting value t by 2 divided by 2 omega, then minus 0 plus, and put the value of 0, it is sine 0 by 2 omega. This will be equal to square root of Vm square by t by 2 minus. This value is 0, sine 0 is 0, so this also has 0. Here 2 and 2 get cancelled, so remaining is sine omega t by 2 omega. This sine omega t is also 0 because sine omega t will be equal to sine 2 pi. We know omega t will have the value 2 pi by capital T. This is the omega multiplied by t. T and t get cancelled, so remaining is 2 pi. This sine 2 pi will have value 0. Therefore, finally we will have the value equal to square root of Vm square by t into t by 2. This t and t get cancelled, and remaining is square root of Vm square by 2, or we can write it as Vm by root 2. This implies that RMS value of the output voltage is Vm by root 2. Now using the value of DC output voltage and RMS value of the output voltage, we can find the efficiency of the full wave rectifier. Efficiency eta is DC output power by RMS value of the input power multiplied by 100. This DC power will be equal to VDC square by RL divided by VRMS square by RL into 100. VDC is 2Vm by pi whole square divided by RL divided by Vm by root 2 square by RL. This RL and RL get cancelled, and Vm get also cancelled, so we will have 2 by pi whole square into root 2 whole square, that is equal to 8 by pi square. On simplifying, we will have approximately 81.2%, and it is almost double of the half wave rectifier. If we redraw the output voltage of a half wave rectifier and also for a full wave rectifier, the shape is sinusoid. In half wave rectifier, we get output for the half cycle, and then there is no output, then again we get output, and then no output, because in first half cycle diode conduct, and in next half cycle diode do not conduct. While in case of full wave rectifier, we have output in the both the cycles, half cycles, but they are also fluctuating. In first half cycle D1 conduct, in second half cycle D2 conduct, then D1 conduct and D2 conduct, and so on. So output voltage is not constant. So to get the constant output voltage, we have to use the filter circuit. These filter circuits are the capacitor, which are connected across the load resistance in parallel, or maybe a inductor which is used in series to a load resistor RL. So if we use the capacitor in parallel with the load resistor, which act as a filter circuit, the output voltage will be improved DC voltage. This will be the output voltage which has filter out the AC ripples and give the almost constant DC voltage. We draw the half wave rectifier with the filter circuit for example, where this input voltage Vs is applied at the primary coil of the transformer, and at the secondary coil, which have a diode as a rectifier, and resistor is RL across which output is taken. A capacitor is connected in parallel to the load resistance. So output will have the better output, that means lesser AC ripples and almost constant output voltage. So capacitor here act as the filter circuit, while the diode act as a rectifier. Let's take some problems. First question is, a PN junction diode can be used as options are condenser, regulator, amplifier, or the rectifier. And as discussed, PN junction diode can be used as a rectifier which converts this AC into DC. Capacitor as condenser, and the Zener diode is used as a voltage regulator, while the transistors are used as the amplifier. Second question is, a full wave rectifier circuit is operating from 50 Hz means the fundamental frequency in the ripple will be. If we draw the waveform of the input and output of the full wave rectifier, the input has AC, which have the frequency 50 Hz. And if we draw the output voltage, the shape of the output voltage will be also having the AC ripples. Here time period is T in the input voltage, while the time period of the output voltage is T by 2. Therefore, the frequency is double of the input voltage because frequency is 1 by time period. So frequency of output voltage will be 1 by T by 2. This is equal to 2 into 1 by T, and 1 by T is the frequency of the input voltage, so it is F in. Hence, frequency of output voltage will be twice of the input voltage, that is 50, so it is 100 Hz. So option D is the correct option. Third question is, a PN junction D shown in the figure can act as a rectifier. An alternating current source V is connected in the circuit. The output current is, and there are the four options. If we see the diagram, this is the half wave rectifier. And in half wave rectifier, we know that diode conduct for one of the cycle when the terminal A is positive, and it do not conduct for the next half cycle. So we can see easily that option C is the correct option. Fourth question is, the peak voltage in the output of a half wave diode rectifier fed with a sinusoidal voltage without filter is 10 volt. The DC component of the output voltage is. It is given that output voltage is having the peak voltage 10 volt into, because it is sinusoidal, so it is sine omega t. If we draw the output voltage with respect to time, we will have output voltage which is sinusoidal for half cycle, and then no output for next half cycle. Then again we get the output, then no output, and so on. So one cycle has the time period capital T. So average value of the voltage or DC voltage is 1 by time period T integral 0 to T by 2, and output voltage is 10 sine omega T dt, and for next half we have the zero value of the output voltage. This is equal to 1 by T into 10 is constant taken out, remaining is 0 to T by 2 sine omega T dt, and it is equal to 10 by T. Integral of sine omega T is minus cos omega t by omega, and limits are 0 to t by 2. So it will be minus 10 by t. First upper limit, it is cos omega into t by 2, then minus cos, and there is omega is also, so it is also taken out, and then 0, it will be cos 0. Cos 0 is 1, and cos omega t by 2. Omega t by 2 will be equal to 2 pi by 2, because omega t is 2 pi, and it will be simply pi, and cos pi will be equal to minus 1. Hence, this value will have the value minus 1. It is equal to minus 10 by omega t into minus 2, or it is equal to omega t is, we have shown that it is 2 pi, because omega t will be equal to 2 pi by capital T. It is the omega into t. T and t get cancelled. Value is 2 pi. So minus minus plus, and it is 10 into 2, 20 by 2 pi, or we can write 10 by pi volt. It is the DC value of the output voltage. Hence option B is the correct option.